Okay, so today we're going to be covering simplifying complex fractions. It's going to be pretty straightforward. There's two methods according to the book. I recommend you read the book because this is going to go fast. Ooh, sorry. What is a complex fraction? A complex fraction is a fraction of the form, ready? Ready? Let R1 to Rn of x be rational functions. Okay? So like polynomial over polynomial, denominator can't be zero, you know, the works, right? Okay. A complex fraction is going to be a fraction where it's r sub 1 of x plus r sub 2 of x, plus r sub k of x. So it's just going to be a series of rational functions added together. The whole thing divided by r sub k plus 1, so just another 1 of x, plus r sub n of x. That's it. That's what they are. So for example, you'll have like 1 over x plus 1 over x squared plus 3 over x cubed all over 1 over x plus 13 over x squared plus x plus 1 over x cubed. Okay? That's all. How do you add them? The way you do every other fraction. Please get good. Okay? Alright, anyway, so I'll show you the two methods to do it. The first method is turn or top into one rational expression, to turn bottom into another, combine like terms, then treat as normal rational division. And then we treat it like 2 lecture videos ago or something like that. Okay, so that's method number 1. Method number 2, which like is fine, is determine LCM of top fractions, then get denominator to LCM, add all fractions, do same for bottom, and then proceed with step 3 from method 1. It's all the same thing. I lied. All right, method 2 is determine the LCM of all fractions, which to be fair, eventually you'll have to do anyway. To get all fractions denominators to LCM, three apply distributive property wherever necessary, combine like terms, leaving you with number 3 of method 1 proceed with step 3 of method 1. I'll show you guys what that looks like. Ready? Okay, so if we use this guy, actually, it's a very good one, if I say so myself. I made it up. I don't know what to tell you. So method 1 is you turn the top and the bottom into, instead of 3 different fractions on top and 3 on the bottom, you just do one of them. Okay. So I see that this is an x cubed, this is an x squared, and this is an x to the first. Okay. We want x cubed. That's easy enough. So our numerator is going to be written as x squared over x squared times x, right? So there's a 1 here from here, right? Plus 1 times, to get this guy to become an x cubed, you multiply by just 1x. X over x squared times x plus, oh look, this is already x cubed. Nice. 3 over x squared x cubed. Okay. And we'll do the same for the bottom. It's the same denominator. I lucked out. Method 1 and 2 are very similar for this specific problem, but you'll see when they're a little bit different, okay? So I'll do this piece quickly. This will give me 1 times x squared over x squared times x plus 13 times x all over x times x squared, right? We just inherit that. Plus, it's already x cubed, we'll just leave it alone. No. X plus 1 over x cubed, okay? Once you have that, you're gonna have x squared over x cubed plus x over x cubed plus 3 over x cubed all over x squared over x cubed plus 13x over x cubed plus x plus 1 over x cubed. All right, and then I'm going to smush it all together. I'm going to go back to my color coding situation. We're going to be x squared plus x plus 3 all over x cubed, the whole thing divided by, let's see, x squared plus 13x plus x plus 1, like that, over x cubed. Okay, let's do some combining like terms. We're going to treat it like any old rational expression, okay? Nothing to do on top. This would be x squared plus x plus 3 over x cubed all over, oops, forgot my parentheses, for this specific problem, parentheses don't matter as much, but I'm going to insist you guys do it because if you don't, bad things will happen to you. Okay? Okay, this gives me x squared plus 14x plus 1. Okay. All over x cubed. And then we're going to keep change flip like our life depends on it. X squared plus x plus 3 all over x cubed. Keep change. I'm going to flip it. X cubed all over x squared plus 14x plus 1. Okay. Now, you see, oh, these cancel out. So we're just left with this numerator and this denominator. X squared plus x plus 3 all over x squared plus 14x plus 1. And I'm going to make you FOIL this out and see if, actually, no, I'm going to make you tell me whether it's necessary to simplify any further. Is there any way to simplify further? Why or why not? Okay, so Gradescope. Can this be simplified further? Okay. Okay, now I'll show you method 2. You're going to see why there's an appeal to it, okay? Now, it doesn't always work out the way you want it to. It's not always as nice. Sometimes it becomes more unwieldy, especially if you have like more factors, okay? But immediately we see, oh, cubed, squared to the first. Come on, right? We could just turn everything to x cubed and call it a day. So, turn everything to x cubed. This gets an x squared, this gets an x to the first, this gets nothing. Okay? So our denominator now becomes x squared plus x plus 3 all over x cubed. Our denominator becomes, well, same idea, x cubed plus 13x plus this gets nothing, x plus 1 all over x cubed, right? And again, now it just looks like step 3 of the other guy, right? Combine like terms, keep, change, flip, so forth, so forth. Okay? The beauty of this, though, is if you make the denominators the LCM, like we did here, when you keep, change, and flip, you get the LCM on top and bottom, and then they cancel out. That's all. Please do a lot of practice. It's I have an old video up. You can find it if you'd like. I'll link it below, I guess. Yeah, they're just a little painful. Okay, for Gradescope practice, I want to pause. Okay. So I want you guys to do numbers 9 through 16, 20 to 24, 38 to 41, and 47. This is on page 121 of your digital textbook, okay?